Okay, so we are very happy to have this lovely lineup of speakers for this two-day symposium on combinatorics and probability. And we will open with Professor Souvik Roy from the ISI Kolkata, who will talk to us about some open problems in game theory. Over to you.
Thank you very much. Firstly, many thanks for the invitation, and I really feel honored to be in this, eminent set of speakers. And in this symposium, whatever I have prepared, it is keeping the students in my mind. So the basic objective of this presentation is to get the students, give the students some exposure on some research areas of game theory. So that is my basic objective, because I have been guiding project students and some PhD students in ISI. So I always felt that students are sometimes or most times they like the game theoretic problems. So that's what I'm going to do. Summarizing, I'm going to just discuss the problem. I won't discuss the solution techniques in deep details, but I will give some outline how the problems are tackled. Okay, so that's it. Let me go to the first thing. Just a second. My screen is. So the first problem I'm going to talk is NEM and graph NEM games. So this is a combinatorial game. A general combinatorial game is one where there are two players, and the players, they move alternatively. So I am playing the game with, say, you against you. Then one of us will be the first player, like chess or any other such board games. I will make a move, then you will make a counter move, then I will make a move, and the game will go like that. And what are the moves that are available to me are predefined at any state. So as we go on, different states are, the different states occur. And at every given step, what I can do, that is given. And based on one of these available moves, I can make a move, and the game goes on till some one of us reach some state which is predefined as a winning state. Okay, this is a very general combinatorial game, and any game that we play like chess, tic-tac-toe, or there are just some special cases of this game. In this presentation, I will discuss two particular type of combinatorial games. One is NEM game, which is solved, and another one is graph NEM game, which is totally unsolved. I will tell you what is the state of the nature of these graph NEM games. And this is a problem that I am working with, of this graph NEM game problem. NEM game is solved, working with Momonti Poddar. I think most of you know her. She is an ex-student of ISI, and Shayar Karmakar, he is also an ex-student of ISI. Momonti is in ISER Pune, and Shayar is in Florida. Okay. Now, what is a NEM game? NEM game is like there are, say, some urns, some boxes. I and you are playing the game. So there are 3 boxes in this example. Each box contains some balls. Maybe first box 6, second one 7, the third one 8. And then maybe I'm the first mover. It is predefined. Then I choose one box and remove some of the balls. I have to remove at least one. I have to pick out at least one ball, but I can pick as many as I want, as till there are some balls. Like I cannot pick more than the available balls in a box. Okay, so I choose one box. I remove some of the balls, at least one from that box. Then you come to play. You choose another box, maybe the same box. Then you remove some of the balls. Then again I remove some of the balls. It goes. The person who faces all the boxes empty, or the person who picks the last balls from all these boxes, like who makes the last move, is the winner. So if at some position I pick all the balls and then you see the all boxes are empty, then you lose the game. Okay, that's the NEM game. Very simple game. You can play this game with your friends. Okay, when I say you, I mean the students. I am here. This whole presentation is, I know I have prepared this presentation targeting the students in my mind. So that's a NEM game. This is this whatever I have said. This is just written here formally. I won't go into those details. This is too simple game. The question is that so the game is totally defined by this configuration. So a configuration means the number of balls and the number of boxes. So it's an integer vector. Not integer, is a positive integer vector. So that's a configuration. Given a configuration, which means given a game Which player will win the game? That is the question. Is it the first player? Is it the second player? Depending on the configuration, or is it always the first player, or what? That is the question. Okay, that
And
is
one
again, let me
question.
tell you. Hello.
Souvik, yeah. So
Yes.
it is a game of perfect information, right? Everybody knows.
Yes, yes. It's a complete information game and it's a perfect information game. It's a
Okay.
common knowledge. The game structure and everything is a common knowledge. Thank you, sir. Thank you for the mention. Yes, it's a perfect and complete information game. And I was just about to say that we can have random versions of these games, which is incomplete information game. I will discuss after this. I will discuss some games called percolation games. There it will be clear what a random version of this game can be. But as of now, it's a very simple, perfect, and complete information game. Okay. So now coming to the and another point, you see here the initial configuration. This is deterministic. Okay. But in general, for random games, which I am going to talk in more details in the second problem, this initial configuration can be probabilistic. So the players, they do not know which configuration they are going to face. And then question becomes that what is the probability that player one wins and what is that player two wins? If there is a possibility of draw, then when it is a draw and so on. So when I'm saying always that what is the probability that player one wins or two wins, I'm not talking about a draw. So that's a question you may think that, okay, why can it not be a draw in this case? But you can see in this game, it cannot be by the definition of this game. Because whoever we have started from some configuration and everyone has to pick at least one ball. So there will be one time when all the balls are picked up. So there is no question of draw, but in general combinatorial games, there can be draws. Okay. Now, for this combinatorial game, this name game, the solution is known. It is known in the literature for quite some time. And the solution is that pick a configuration. So this A1, A2, AN, this is suppose there are N boxes and the number of balls in the first box is A1, that in the second box is A2 and so on. And if the XOR means the binary sum, if the XOR operator of these numbers, A1 plus XOR A2 plus XOR dot 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 XOR AN, if that is 0, then the game is a losing position. That means the first player will lose the game. Okay. So you can see the proof or the idea is one side is very simple, I will tell you. But general, it is not so intuitive. Why the answer to this question is related to the XOR operator, XOR sum operator. I will give you some intuition, but at least I am just making the point here that it is not so straightforward. But anyway, the answer is that you start with the configuration, you have some integers. Basically, you start with a positive integer vector. So you have, say, n many integers. You take the XOR sum. If that is 0, then for that configuration, the player one will lose. Otherwise, player one will win. So that's a known solution. And you may think, as I have said, that one side of this solution is kind of intuitively understandable. That is that if the XOR sum is 0 to begin with, then no matter what player one does, player two again change. So player one, what player one will do? He will reduce one of the numbers. That's basically the game, how the game goes. Then player two can change another number to make the XOR sum again back to 0. So that's how player two can always ensure a win and player one will always lose. So that's one way to that when the XOR sum is 0, why player one will always lose? That's a simple argument, and kind of the same argument works to show that if it is not 0, then player one will always win. Kind of the same argument. Anyway, this is kind of an exercise. I normally give my students this problem as an exercise. If you start working with this problem, you will immediately see that how this comes, and it will take you 15. When I say you, I mean the students, 15-20 minutes to figure out this problem. And I have given this problem to project students, and they have done it. Now comes the problem that we are working. This is a graph name game. This is a generalization of the game I have talked about. Now, instead of I have before I had say n boxes. Now think these boxes are associated, and in some way. So there are first box, second box, and third box. They are associated, and then some other boxes are associated. They do not need to form a partition also. And at every turn, you can pick one association, and then pick any number of balls from all the boxes that are associated. Okay. To represent this game in a simpler form, let us consider a graph. Look at this graph. We have vertex 1, vertex 2, vertex 3, and vertex 4. And this graph, this gives the association. That means vertex 1 is associated with 4, with 3, and 2. This is a complete graph, but in general, the graph doesn't have to be complete. Okay, now you start with a graph. Each edge has some positive weight, integer, of course, positive integer weight. So the edge between vertex 1 and vertex 4, the weight is W1, say that is 3, say W2 is 5, and so on. Okay, so we have weighted graph. Now, how the game goes? Suppose I am the first player. I pick one vertex and I see all the edges that are incident on that vertex. And then I can pick any number of balls from, or any number of weights, whatever you choose to call it, from the incident edges. So if I pick vertex 1, then I see I have these many incident edges, but 2 vertex 4, 2 vertex 3, and 2 vertex 2. So then the available edges from which I can pick some number is W1, W5, and W2. Now I can pick one perhaps from W1, so this becomes W1 minus 1. Maybe 2 from W5, it becomes W5 minus 2. Then maybe 3 from W2, it becomes W2 minus 3. I'm assuming all these numbers are bigger than 1, 2, and 3. Okay, so this is the game. I have a graph. At every step, I pick one, I choose one node. Then I see all the incident edges from that node. And from those edges, I pick some number. I can pick any collection of numbers from these incident edges, but I have to pick at least one number. Okay. So you can immediately see this is a generalization of this name game. Now this game, this becomes, I would say, quite combinatorially a challenging problem. The reason I'm saying this is a long open problem. A well-defined, well-declared open problem. And this problem, when there are 4 nodes for all those graphs, when there are 4 nodes, this problem is solved manually, like case by case. So with 4 nodes, you know that there can be so many graphs and so many weights on that graph. So you have too many cases. But of course, you do not need to analyze each of these cases separately. You can first fix the graph structure. Maybe it's a cycle, maybe it's a path, maybe it's a complete graph. And then you can see some class of weight distributions on the edges, and then you can analyze. But the existing literature on this problem is that for 4 nodes, manually, case by case, the answers are known, that were known in the literature. Then we started working on this problem. And then for 5 nodes, we have again manually found all the solutions. But in general, I'm telling you what we know a bit. In general, finding a general solution, it turns out to be, at least as of now, we do not see any, we do not have even an intuition to how to give the solution for a general graph and a general weight distribution. So the things that are
what is the range of
no range? It can be anything. It can be anything. Any positive integer. There is no limitation. There is no restriction on that.
There are 450 number of edges, so we cannot put more than 450.
No. If it is the graph need not be complete. It can be any graph, and for each edge, you can choose any positive integer as the weight of that edge, and then you get a graph name game. Okay.
Then you can include 0 for the weight. 0 weight.
No, not 0. A positive integer. Positive integer. If you give 0 weight to some edge, it is equivalent to not having that edge. Yes. Because we are drawing the edges, so positive integer. For every edge, you define the weight of that edge as some let's say natural number starting from 1, 2, 3 up to any number. Is that clear?
It is clear. But my point is that if you consider the full complete graph and put and allow weight 0 also, then you can get non-trivial graphs also.
Yeah. It's another way of saying the same thing. Yes, but why will you do that? It's just
I just try to associate.
Yeah, of course. Absolutely true. Of course. You can just draw the edge and put the weight 0. You can of course do that. 100% correct. Yes. But the thing is that it's like seeing a simple graph, say a path graph, as a complete graph with many 0 weights is graph theoretically not so convenient. That's what I can say. For instance, we have solutions for path graphs, for cycles, for some regular graphs. But if you want to see a path graph as a complete graph with many zeros, it's just inconvenient for you to analyze. It's just that. But it's the same thing. I mean, having 0 weight on an edge is equivalent to having not having that edge. But you are right. Okay. Is that clear now?
Yes, yes.
Sure. So I'm wondering that in this case there can be draw, right? Like if the balls number of balls becomes less than the weight, then there can be draw.
I do not get you once again. So at every time you are reducing the weight distribution of the graph, everybody is forced to reduce it by at least 1. So it will reduce every time.
No,
then at some point it will go to 0, and whoever reaches that 0
is the role of
is
the weight. Like you have to remove the weight number of balls from the neighborhood, right?
Yes, the weights is basically the number of balls on that edge. So each edge is now kind of a box or neem or urn, and removing weight is basically removing some balls from that, and you have to take at least one ball. So at every turn you fix one vertex, and you see all the edges that are associated with it, and you have to pick at least one ball from all these edges. So you can pick, suppose you have 3 edges available to you. Your choice is to choose one number, say x1 from the first edge, and x2 number of balls from the second edge, and x3 number of balls from the third edge, such that x1 plus x2 plus x3 is greater than or equal to 1. That is this. So you have to pick at least one ball altogether, but you can pick any number of balls. Huh?
Yeah. So what is the role of weight? Then xi should be less than or equal to wi, the weight I.
Yes.
Okay.
Yes, that's the weight. Weight is basically number of available balls in that edge, on that edge. So each edge you can see as the box, and weight is basically the number of balls available in that box. And of course, you cannot pick more than the available balls. So weight is basically the number of balls available, and every time it is reducing. Not like everyone is reducing, but at least one weight will reduce.
Okay.
There is one question on the chat, which is it known for trees?
I'm telling you what is known. Okay, this is a very, I will say, very open problem. I'm telling you here. I'm just giving you what is known. So one is path graphs. The simplest graphs you can consider in this framework is paths. Okay, there can be even more simpler, like where all the edges are disjoint, but simplest non-trivial ones are paths. Okay, now for the paths, when all the weights are equal. Okay, so here you'll see the next second point. So when Pn is the path, or n is the number of length, and all the weight lengths are equal, then it is always winning. So the first player, and the winning strategy is also very simple. So the first player will always win. So for those graphs where the graph is a path and the weights are all equal, then it is winning. That's one thing that is known. Not very, I mean, it's simple. I would say, I won't say simple, but not very hard to find this. Then you may consider.
Souvik, I'm just sorry. So you said like the weights are like the current configuration. So it is changing, right? So it is not the one is fixed for always.
No. Yeah, it's changing. The graph, the game is defined by the initial configuration. Then it will change based on the strategies of the players. So when I say that all all weights are equal, the initial
configuration.
Yes.
Okay,
yes.
fine.
Okay. So then you may think of cycle graph. That's one like kind of simpler graph with a simpler structure. And then if it is a cycle with equal weights, then it is winning. Just a second. Then it is, sorry, my Zoom screen is guarding me. When n is even, and when n is odd, then it is losing. So for cycle graphs, also it is the answer is known. We have done, but these are, I won't say these are major contributions. So I say minor results. So for cycle graphs, when there are even number of nodes, then it is winning. When I say winning, it is winning for the first player, and otherwise it is losing. Okay. Now for general setup, then for, as I have said, when there are at most 4 nodes, then it is analyzed by case. It's just like by searching all possible cases. And when it is at most 5 that we have done, again, case by case, but it's a very tedious thing, so many cases and so on. And in general, except for those cases that I have said, and some more cases we have, in general, for instance, if it is a regular graph, if it is a tree, if it is even general path without configuration which has all equal weights, in those cases, to the best of our knowledge, it is not known. I think it is not known because I know people who are working in these areas, and they also don't think that it is known. So this is one problem I wanted to introduce. I will go to the next problem now. I hope the problem is clear, and you can try this problem at home with the graph. Then after playing this game with your friend for some times, you will see that it's a very lengthy procedure. That much at least you may say. For small weights, you can do it, but for arbitrary weights, saying something, even if the graph has, say, suppose 6 nodes, for 5 nodes we have solved it, you will see that how the game will go. Because one important thing is that the winning thing, you cannot immediately see whether a graph is winning, whether a game is winning, because winning means the player 1 has a strategy such that no matter what player 2 does, player 1 will win. That's a very thing. So you maybe by playing some strategy, you are player 1, you are losing, but by that you do not know whether it's a losing for you, losing game from you. Maybe there is some other strategy. So it's like a chase. You really have to think a lot to be convinced whether it is a winning game for you. I mean, you have to find the best strategy also. So that's like the summary of this game. Now I will go to the second problem. Apurva, how much time I have?
Yeah, you have at least 40 minutes or so. Slightly 5 minutes. Or so.
Okay. That was my calculation. Now it is the next problem is Percolation Game, and you are again. My intention here is to make the students, the ISI young undergraduate students and the postgraduate familiar with game theory problem. This Percolation Game, as the name sounds, it involves a bit measure theory and some advanced probability. I will skip those. I will introduce the game and I will tell you how it becomes a bit challenging and what are the problems and so on. So Percolation Game is basically a game on a random graph. Okay. So let me first consider the simplest graph. But again, I'm telling you, this is one special game I am here presenting. It's the general class of games are very unexplored. Even this special game is not explored. Again, this is a problem that I'm working with Momonty Shire and a PhD student of Momonty. So, and one more thing, we are working on 2 different problems in this area. One is node percolation game problem, another one is edge percolation game problem. I will explain briefly both of them. So let us consider the simplest graph that we can analyze for this game. That is the lattice Z2. Okay, I hope you all are familiar with the lattice Z2. And take 2 probabilities, P and Q. Their sum is less than equals to 1. And this is sorry, my own screen is somehow blocking me. Just a second, I don't know how to fix it. Just a second, my own. Okay. Okay, so fix 2 numbers, P and Q, that are probabilities whose sum is less than equals to 1. Okay. Now you have Z2. Each node, we are calling it a site. Each node, you call it a trap with probability P, target with probability Q, and open with probability 1 minus P minus Q. Okay. So you have Z2 for each node. You conduct some random experiment, and depending on the outcome, with probability P, you call it a trap. With probability Q, you call it a target. And with the rest of the probability, you call it just open. Okay, now the game starts. So you get a random graph. Now the game starts with 2 players, say player 1 and player 2. Now they will, as I'm saying, in any combinatorial game, player will make alternative moves. Suppose player 1 starts the game, begins the game. And the game can start from any vertex without loss of generality. Let us assume that it starts at 0, 0 from the origin. So from the origin, and now I'm defining the flow of the game in a general way. Suppose there is a token which is initially at the origin, and each player has to move the token in the positive direction. I will tell you what is the positive direction. It will be available immediately clear. So everybody has to move the token. And in general, suppose the token is at the node ij. we're in Z2. So if you sorry for the noise, I'm very sorry for the noise. As I've told you that I'm outside, so I cannot control these things.
Actually, I can't hear anything. Don't worry.
So suppose the current token is at the point ij. Now there is a player, maybe player 1 or maybe player 2, who is now has to make a move. I mean, has to move the token from ij. Now, for the point ij, there is a function which is aij, which may also depend on the player. I'm making it simple, which is aij, which says what are the available nodes where the token can be moved from the position ij. Okay, that is given by this is a function. It may depend on the player. So for player 1, maybe there is a function a1ij. For player 2, there is a function a2ij. So suppose you are player 1, you come to this is your turn. You see the token is at ij. Then you look at the function aij, and that tells you that what are the positions that are available for you to move the token. And then now it is your strategy, game theoretic strategy, to move the token to one of those positions in aij. Okay, so that's how the game. The problem we are working there, aij is very simple. Okay, it can be even simpler. That is that from ij, you can move the token to a node which is at most at a distance of 2. So in the positive direction. So what is aij? I plus 1j. That means you are moving the token in the horizontal direction by 1 distance, or j plus 1 in the vertical distance by 1, or I plus 2j, or I plus 1j plus 1, or ij plus 2. So at every time, in any player can move the token at a distance at most 2. That is the game we are considering here. And now, what is the rule of the game? If a player is forced to move the token to a trap, then that player loses the game. If the player can somehow manage to move the token to a target, then that player wins the game immediately. He is the winner. And if the game continues, so if it is an open node, so you are in a node which is neither a trap. Hello? Yeah. Okay. Trap, then the game will continue. Okay. Now the important question here is that what is the probability that the game will end in a draw? Okay, that is not the most important question. Another important question is what is the probability that player 1 wins the game or player 2 wins the game? But before coming to that, even finding the draw probability is a challenging problem. Now, only one paper is there, which is by Holroyd and Markovici and Martin. I will call it HMM paper. They consider a much simpler version where the available nodes, available moves from the point ij is I plus 1j and ij plus 1. So you can move the token only by at a distance 1. That's simple. So it's the simplest possible percolation game. In that case, for that game, they have shown that for any p and q positive, so as long as the probability of trap and target, they both are positive, each of them is positive, then the corresponding, okay, this PCN thing I will explain for the students. Please don't ignore this part that something is ergodic, ignore that part. But this part, the draw probability is 0. So in this simple case, the game will never end in a draw. Okay.
So what is a draw here? What is the winning and losing configuration? When do we call it a draw?
No. It's a graph on a random configuration. Now fix the configuration, okay, which is drawn randomly. Now in that configuration, player 1 and player 2 are moving. Every time a player is moving, he or she is trying to reach a node which is a target. And okay, so is the other player. Okay. And somehow, if you are, so it's like a chase. If somehow I play the game in a way that now you have to move every time, you have some available moves, but all the available moves are traps, then you lose the game because you ended in a trap. Okay. Or if you somehow reach a target, then you win the game. But if this is not happening, you are in a node which is neither a target nor a trap. It's just an open. Every node is also defined as an open node. It's just an open, then after I will make it move, and then I am also in an open node. If the game continues like this, which means essentially that there will be an infinite path, but having an infinite path is not sufficient because players are strategic here. That's the difference between percolation games and percolation. In percolation is the probability of having an infinite connected component of 0 is the percolation probability, but here that is not the case. And that's why the draw probability is 0. In general percolation, percolation on Z2, the draw probability or percolation probability is not 0. So that's how. So the game open means implies that there is an infinite open path, but that's not sufficient because maybe there is an infinite open path, but neither of the players will follow that path. Every player wants to win and avoids to lose. Okay, is that clear now?
Yeah, thank you.
Just one question, Souvik. One question.
Yes, yes.
On the previous slide, you said distance at most 2, but you did not say I minus 1j, I j minus 1.
True. No, here I just said that it's at most 2 in the positive direction. So in the positive, by positive direction means either in the horizontally positive direction or in the. So this is just a problem. In general, I have said that Aij can be anything, but even for this problem, I will come to the next problem which we are working. Is open and is seemingly we have almost solved. I will tell you the state of the nature. But my general point is that here we are fixing this as the available nodes from Ij. So I have called them that nodes that are available at a distance 2 in the positive direction. But in general, they do not have to be in the positive direction. You can have loops and so on. It's a bit problem if you have loops. The draw probability is normally positive, but in general, you can have. Okay. Now, so this is the HMM problem. They have shown the draw probability is 0. Now, the problem they have solved, or this kind of problems, they are normally analyzed by using probabilistic cellular automata, and which we call in short PCA. And I will not go into the details. I think it's better to present other problems. But roughly speaking, this is you start with a configuration on Z. So the state space is 0, 1 to the power Z. So you each node, each point on Z, you label them as either 0 or 1. And every time you modify the configuration, looking at the nodes that are, so whenever next time you will determine the level of a node. So eta t plus 1n, and then it can be either 0 or 1. That probabilities, whether it is 0 or 1, depends on the configurations, the time before of its configuration and its neighbor. So suppose you are at, suppose you want to define, you want to know the level of the node 10 tomorrow. Then you will see what is the level of the node 10 today, level of the node 9 today, and then randomly you will define the level of the node for tomorrow. So that is standard PCA model. And the game they HMM has considered that has boiled down to this PCA, which is relatively a simpler PCA. And then they have shown using this PCA, they have shown that this PCA is ergodic, periodic, and all this. They have done some. Its general strategy is constructing some weight function. I will not go into the details. I'm just naming those things. And with all these things, they have shown finally that the draw probability is 0. But now the problem we consider that induces, that is again a PCA model in a probabilistic framework, but it's a complicated PCA model. Here, the difference is that if you want to know the state of a node tomorrow, then it depends, of course, randomly on the state of that node today, of its neighbor and of its second neighbor. So the state of the node n at t plus 1 depends on the node state of the node n at t, n minus 1 at t, and n minus 2 at t. And a bit surprisingly, the PCA model with 3 steps is not solved in the literature. The other one was also not solved, but this is very significantly different from the other model. So our game actually forces us to work with this 3-step PCA. And we have been working on this problem. We have shown this problem is more or less we have solved. And I must say that Momonti has done a great job in solving this problem. She is like super, she has superpower in doing calculations. I think it involved, I don't know how many pages of calculations. It turned out to be extremely calculative problem in calculating some weight function and so on. And probably more than 20-30 pages of calculations he had to do. And we were like, we didn't know where we are heading towards while doing these calculations. But finally, for most P's and Q's, we have shown that, okay, when Q is 0, P is positive, we have shown it. When P is 0, Q is positive, we have shown it. When P and Q are both positive, then for most values, we have shown it, and we can now see that we can show it for arbitrary P and Q positive. So we are hoping to get the result that here also, if P and Q, each of them is just positive, then the probability of draw is 0. Okay. And then there is another problem here I have just mentioned, which is age percolation problem. In percolation, if any of you know percolation, then you know that there is bond percolation and then the site percolation, or I call it node percolation and age percolation. The game can be also defined for age percolation. That is also we are working, but on age percolation, it becomes even harder. All these things that we have done here are not helping us much there. Okay. So summarizing, percolation problem is a game on a random graph. The first one was a game on a deterministic graph, much simpler. But this is now a game on a random graph. There can be numerous games on random graphs. The simplest one is solved. The next simple one, where player can move up to 2 distance, or the game is defined on ages, are not solved. And we are working. And if you any of you are interested, we have, I think, more or less a draft and some results we can discuss. Okay. Now I will come. Apurva, how much time do I have? Hello? Hello? Hello?
Yeah, we can hear you. Sorry.
Okay. So how much time do I have?
20 minutes at least.
20. Oh, that is fine. That is fine. Okay. I thought my internet connection, my internet got disconnected.
No.
Okay. Now, so now I will discuss a problem which is purely combinatorial problem. The other ones also combinatorial, but probabilistic. But this problem, at least the definition of this problem is purely combinatorial. Okay. It is coming from some game theory. I will give you the game theoretic story, but mathematically is a very simple problem. But at least to me, is a hard problem. I have solved in many cases, but in general cases, I cannot. I have not been able to solve. Or many other people are also working. They also, at least as of now, there is no solution in the literature. So say A1 to AM is a set of M choices or outcomes or objects. Now it's more game theoretic. Okay? It's like a general number of pairs and so on. So there are M objects or outcomes or choices. And R to the power M denotes the set of all possible valuations of these objects. So A1, A2, AM, suppose M is 3. There are 3 objects, a laptop, a mobile, and a computer. Okay, so there are 3 objects and you are a player and you have some possible valuations for these 3 objects. For laptop, your valuation, these are given objects, 50,000. For the computer, say 20,000. For the mobile, say 10,000. Okay, this is just a possible valuation. Now, D is the set of some possible valuations that a player can have. Okay, here I am considering a game with 1 player. Of course, we do not do games for 1 player, but just for simplification, you will see even with 1 player what this game is. Okay. Now, a decision rule is a function from D to A. So what a decision rule does, I have 3 objects. You tell me what is your valuation for the laptop, for the computer, for the mobile, and seeing your valuations, I decide to give you one of the objects. That's a decision rule. So this is a mapping from D to A. Okay. Now for this decision rule, so it's a purely mathematical function. Even if you don't care about game theory, you can see it is very simple mathematical function. Now this decision rule, it will said to satisfy K-cycle monotonicity. In short, it is KCM. If for every K points from the domain T1, T2, Tk, we call them T because in game theoretic language, these elements are called types. But anyway, so for every sequence of K points from the domain, you have this condition. So what is this condition? That you look at the outcome of F at, say, for instance, T1, and then you see your valuation of the outcome at T1. So the left-hand side is T1 of FT1 plus T2 of FT2 plus FT3 of FT3 and so on. So once again, game theoretically, what is this? You report me your true valuations for the objects and I give you some object. T of FT or Ti of FT1, it gives you what is the valuation you finally get. For instance, you say your laptop is 50,000, computer is 20,000 and mobile is 10,000. And I give you the computer. Then what is the valuation you get? That is 20,000. So that is those numbers are here. And I have fixed beforehand arbitrary K points or types from the domain, and I am calculating the total valuations or utility you can get. This is. And on the right hand side, I'm calculating the same thing, but not doing the direct evaluation. I am doing the evaluation of the outcome at T2 when your valuation is T1. So if you see this, it is basically T1 of FT2 plus T2 of FT3 and so on, and then finally Tk of FT1, because Tk plus 1 is 1. So I am first doing the direct evaluations and then doing the cross evaluations or shifted evaluations. So I evaluate the outcome at T2 using the valuation at T1. Okay, this is a mathematical condition. But why are we interested in this mathematical condition? Now I'm coming to that. Now, you see, in game theoretic thing, what I am doing, I am constructing a function f that will give you some object based on your valuations. And for such a function, I want some property called implementability. Okay, that's a property. And basically, the game theoretic definition is that if there exists a price function or payment function that is again from D to R. So for every object, D is the types. So for every type or for every object, I define a price such that whatever valuation you are getting. So beforehand, I was saying that I will just, you give me your valuations, I will give you an object. Now I'm saying that no, I won't give you the object for free. I will also charge you some price. I know your valuation, I can charge exactly that price, but I do not need to charge exactly that price. I can charge something less also. It depends. In shops, that's how it, or in any business, that's how it works. So if you can find a price function such that once you report your valuation to me, I give you some object, then Ti of FTI or T of FT is the valuation you get from the object I give. Then it is the price you pay for getting that object. And this is your net valuation, like after paying the price, whatever you get as benefit. If that is greater than this quantity, and what is this quantity? Now you are thinking, because it's game, your strategy, you are thinking that instead of telling the true valuation, if you go to a shop, will you tell your true valuation? You will say, you will lower your valuations so that I do not charge you a higher price. So now you are saying that if you report something different, maybe lower, maybe higher, whether that will benefit. And this implementability says that I have defined the price function in such a way that it is better for you to report your true valuation. If you report it any other way, suppose your true valuation is Ti, you report it as Ti prime, then whatever net utility you will get, that will not exceed the current valuation. Okay, now you can forget all these things. Just know that there exists some game theoretic property, some equilibrium property, which by means of this theorem makes it very important to study KCM functions. So this theorem says that a division rule is implementable. I have given you some impression of what implementability is. It is basically making it an equilibrium in some way. It's just having a game theoretic equilibrium. But even if you don't get it very clearly, but just know that we want to achieve equilibrium, and there is a theorem that says that K cycle monotonicity for all K greater than or equals to 2 is equivalent to having an equilibrium. So now whether a division rule lies in the equilibrium or not, to know that, you have to check K cycle monotonicity for every K greater than or equals to 2. Now, if I give you a division rule, that's a function from, you remember, this is a function from D to A. D is a subset of R to the power M. And then from this D, you can consider so many, even if fixed 2, there are so many pairs of elements, so many triplets of elements, and so on. And you're able to check K cycle monotonicity for every K. That's even computationally very difficult. Okay, so this method is not so useful as of now. But now comes the very important mathematical problem. Is it really necessary to check K cycle monotonicity for all K greater than equals to 2? Or somehow after checking some steps, it is sufficient? So it is the case that if you check K for K, 2, 3, 4, and 5, then you are done. If for these Ks, cycle monotonicity is satisfied, then it will continue to satisfy for higher Ks. That is a very important question. Even more specific question is it possible that if you just make a division rule satisfy 2 cycle monotonicity? Very simple. 2 cycle monotonicity means for every pair of points, X and Y, if you calculate X of Fx plus Y of Fy, that will be greater than or equal to x of fy plus y of fx. So that is two-cycle monotonicity. Is a very simple condition. So is it somehow possible that if you just make a rule satisfy two-cycle monotonicity, it will continue to satisfy k-cycle monotonicity for all k? If it is, then why? The answer depends on D. And now comes very interesting answers. If D is convex, then this is indeed the case. So if D is a subset of R to the power m, if D is convex, then it is indeed the case that two-cycle monotonicity implies cycle monotonicity for all k. This is an existing result. I have not proved it. The proof is very tedious. I have always felt that perhaps using some elegant mathematics, it can be proved in a simpler way. I have not tried, but I always want mathematicians to give a very elegant proof. The existing proof is very tedious. It's very hard to follow and very lengthy. And proving this thing for, let's say, 3 or 4 or 5 dimensions is not so difficult. Using geometry also, it can be done till 4 dimensions. I mean, till 3, of course, but till 4 also it is possible. But after 4, of course, even when 4, you cannot do geometry. But after 4, some simpler methods are not working. So this is a problem where I think mathematicians, I would like to have a simpler, elegant proof from the mathematics. But okay, at least we know when D is convex. What happens when D is not convex? In particular, what are all domains, all subsets of R to the power m, where two-cycle monotonicity implies k-cycle monotonicity for all k? That's a very important question in game theory, very important. Now, I have worked in this area, many specific domains I have shown where two-cycle implies k-cycle, and some domains it happened, turned out that 2 and 3 together imply k-cycle. So not just 2, but you have to come, you involve 3 also, but you don't have to go far. But and then I can also construct artificial domains where you need to go 2, 3, 4, 2, 3, 4, 5, and so on. But if you give me a very nice geometrical domain of subset of R to the power m, a nice structure, and then ask me what is the monotonicity number, cycle monotonicity number, like what is the maximum number of cycles I need to check for this, I don't know, or also the literature doesn't know. Okay, that's another important problem I wanted to discuss. And now, very similar, Apurva, I think I have 5-10 minutes, right?
10 minutes, yes.
Or 10 minutes, okay, very fine. So I am within my time limits then. Then another problem, which is very related, it is local global equivalence. Okay. So in mathematics, in game theory, what we do basically, we try to combine mathematics, the approach or the line of thoughts of mathematics to our game theoretic solutions. In game theory, we are always trying to characterize equilibrium, and we sometimes, instead of directly characterizing it, we sometimes give an indirect or partial characterization, and this is one related to that. As the name sounds, local global equivalent. So some global property, something which is an equilibrium globally, we want to see when, showing that it is a local equilibrium, when is it sufficient to ensure that it is a global equilibrium. Okay, so that's a kind of problem. And in mathematics, we always know that local integrability when it is equivalent to global integrability, and local maxima when it is equivalent to global maxima, and so on. It's the same spirit. Okay, so we have a finite set of objects as before. Then we have, okay, this P is the set of all preferences of these objects, just the orderings, permutations. So P is the set of all permutations or preferences or rankings on this finite set. And a subset of P, we call it a domain. And normally these are the notations for denoting the elements of D. So basically this squiggle, they are basically some ordering of the elements of A. Now, so I am defining a graph. This is a graph theoretic problem. The graph has the set of nodes is the set of preferences. So the domains. So I have started with the set of preferences. Now I have a graph where the nodes are these preferences, and I am drawing an edge between two preferences if they differ minimally. So suppose you have 3 objects, A, B, C. And what are possible preferences? A preferred to B, preferred to C is a preference. B preferred to A, preferred to C is a preference. C preferred to A, preferred to B is a preference, and so on. Now, from all these preferences, I will draw an edge between two preferences if they differ minimally. This A, B, C, A preferred to B, preferred to C, and B, A, C, B preferred to A, preferred to C. These are minimal, they differ minimally. So A and B, they are swapped. Then I will put an edge between those two preferences. So I have a set of preferences, and I am drawing a graph. by just joining those who differ, those pair of preferences who differ minimally. So I have a graph. Now, for instance, this is a graph where the set of objects is A, B, C, D, E. And this is a preference. When I write it this way, it means that A is preferred to B, B is preferred to C, and so on. And these are 5 preferences. And you see the graph here, I did not, it's a path graph. These two, there's an edge between these two, there is an edge between these two, and so on. So there is an edge between these two preferences because in these two preferences, only A and B, they have swapped. The order here, only A and C or D and E are swapped, and so on. So this is a graph, and you can see there is no edge between any other two preferences. So when the domain is these 5 preferences, then the graph I obtain is the path graph or line graph, which is in this order. Okay, so this is just an example. Then I have a choice function, then which is a mapping from the set of preferences domain to A, the one object. So for every preference, it will give an object. Okay, now I'm defining strategy proofness, which is a game theoretic equilibrium condition. It says, so you just remember that what the function does. I give you a permutation, it gives you an object. That's the function does. So this squiggle or this squiggle prime, these are all permutation. Now it is strategy proof if it is kind of monotonic. It's a monotonicity property. So f of squiggle, that is an object. And now think of any other preference, say squiggle prime. So f of squiggle prime, that is another object. Now you are, because f is defined on squiggle, the object which is obtained by f of squiggle will be ranked above, weakly above, it might be the same, than the object which is defined at squiggle prime. So for instance, suppose the squiggle is the preference A preferred to B preferred to C, and f of squiggle is B. Then if you give me any other preference squiggle prime, f of squiggle prime cannot be A. It can be either B or C. That is, this condition is. Okay, so f of squiggle prime at any squiggle prime cannot be better than f of squiggle according to the preference, the squiggle. Okay, you can see this is a monotonicity property. You can sense this is a game theoretic equilibrium property. You can sense all these things. For the time being, I have a mathematical object, which is a function from permutations to object, and it satisfies this very simple mathematical property. Okay, now I am defining local strategy proofness. If it is strategy proof, here I have defined strategy proofness for a pair of preferences. Now it is locally strategy proof if it is strategy proof for every pair of preferences that form an edge. And it is strategy proof if it is strategy proof for any pair of preferences. So local means only on the local preferences that who form an edge, and strategy proof, or we call it globally strategy proof, if for any pair of preferences, they do not need to be an edge. Now comes the immediate question, when? So for which domains, which set of preferences, local strategy proof is equivalent to global strategy proof or strategy proofness. This has been an open problem for long, and I find this problem is a totally combinatorial problem. You cannot do, okay, I cannot say you cannot do, but apparently I cannot see any mathematics, anything I can use. My object is a function from permutations to objects, and I have a monotonicity property, and I want to see, not just that, I have a graph. I want to see when having monotonicity on the graph is sufficient to having it all over the domain. So that's what the question is. So, so characterizing all the domains that are like in the graph theoretical way, for that are LGE, like where local strategy proofness will be equivalent to global strategy proofness. That is the main question. In particular, if you consider the domain as the full set, suppose you have all the orderings, is it an LGE domain? These are some questions. But anyway, this question is solved. It is my paper with my PhD students and some of my co-authors, where we have characterized all the LGE domains. So all the domains on which this local strategy proofness will be equivalent to. This has been an open problem for long, by the way. So local strategy proofness will be equivalent to global strategy proofness. It involves the presence of some paths in the domain, which looks, I mean, I cannot really give you an intuition. It's a bit complicated, but anyway, the answer is known. But okay, even if this answer is known, there is a very important open problem that is here. What happens for random choice functions? Okay, at this moment, you know, my choice function is a mapping from D to A. You can, of course, we are in a probability symposium, and you all know that you can define a random choice function, which is a mapping from D to probability distributions on A. And then you can define all these things. In the literature, their definitions are there. Then for random choice functions, what are the domains that are LG? That turns out to be, we are working, we have some minor results, but it turns out to be, to us, at least to me, extremely difficult. I won't say extremely, very difficult, to me at least. I mean, these ideas, these methods, approaches, they do not help anywhere. Though we have, for some particular graphs, domains, we have solutions to this problem. Okay, so this is, once again, this is an open problem, exploring the equivalence of local equilibrium and global equilibrium for random decision rules or random choice functions. Now, my last problem, and here you see, till now I was overtly simplifying my problem to one player. Even for one player, the answers are not known, but I want to discuss at least one problem where there are many players. Again, this is one very special case of a very general class of problem. But let me discuss this special case. It will be understandable for you. It's a matching problem. Okay, so let me start first. There is a set of n players. Suppose n is 3. I have 3 players, and there are 3 objects. So there are 3 players, say 3 students, S1, S2, S3, and there are 3 rooms, R1, R2, R3. Okay, and I want to define a matching here. So these 3 rooms will be given to these 3 students. It's a matching, in a sense, it's a bijection, because I do not want 2 students to share a room or 1 student to get 2 rooms. Okay, so I want to form a bijection between the students and the room. It's a standard matching. Okay, now each student has a preference over the rooms. So how do I decide the final allocation? I'm a game theoretic person, so I say, okay, you tell me what you want. So each student comes to me and says that, well, I want room 1, then room 2, then room 3. Second student comes that, okay, room 2 is my best, then room 3, and then room 1. And they each come to me and report me their preferences. So this squiggle I denotes the preference of, say, player I. Then D is the set of admissible preferences. By admissible, I mean, if I have some prior idea what preferences they can have over the rooms, that is D. I may not have any idea, then D is the set of all preferences. For instance, in this situation, I know that they can have any preference. So in that case, D is the set of all orders, all permutations of these objects 1 to n factorial. Okay. And then this squiggle n, suffix capital N, is the set of preference profiles or collection of preferences. That means that what is the situation for me? Each player is coming to me and report his or her preference. So I get a collection of preferences, and that is this squiggle n. So squiggle 1 is the preference of player 1, this is preference of player 2, and so on. Okay. Now, I'm defining it. I have already defined a matching, which is a bijection. I defined it as a bijection, but you can see it as a bistochastic matrix. Rows are indexed by players. Columns are indexed by the objects. So rows are players like student S1, S2, S3. Columns are rooms, R1, R2, I3, R3. And a bistochastic deterministic matrix, I can define a matching. So for the first row, which means student 1, I make 1 at 1 for 1 room and 0 for other rooms. That means that student gets that room. That means that room is blocked. So in that column, I cannot put any more 1. And for that row, for the student also, the student is also got a room. So I cannot put 2 ones in a row. So this is a bistochastic matrix. Bistochastic matrix means in any row and any column, there will be, over here, deterministic bistochastic matrix means in any row or any column, there will be exactly 1, 1. So at every cell, I'm putting either 0 or 1. And in any row and any column, it will be exactly 1. That is a deterministic bistochastic matrix. But you can immediately define a probabilistic bistochastic matrix. Actually, bistochastic matrix, you all know that, I'm sure. It is basically a matrix with probabilities such that the row sums are 0 and a 1, and column sums are also 1. I'm sure here the students can very well know bistochastic matrix. Okay. So I am defining a random matching which determines as an outcome a bistochastic matrix. Instead of defining a bijection, I am defining a random outcome through a bistochastic matrix. Okay. Now, the set of all bistochastic matrices I am defining by, say, this calligraphic M. Also, this calligraphic M by the set of all bistochastic matrix, and a matching rule. A matching function is a mapping from the set of preference profiles to bistochastic matrix. So I have a function that tells me when you report your preferences, you all report your preferences, which bistochastic matrix I will pick. Okay. Now I am going to define some condition called strategy proofness of first order stochastic dominance. This is also something you people know more or less in statistics, I'm sure. But roughly speaking, it says that you have a preference. Suppose you are player 1, you have a preference. Room 1 is preferred to room 2, preferred to room 3. And I am defining some outcome, random outcome for you. So basically, for you, you come to, so your player 1. So the outcome, the row for the first row corresponds to your outcome, and first row is a probability vector. And suppose that probability vector is 2/3, 1/3, 0. That means you get room 1 with 2/3 probability, room 2 with 1/3 probability, and room 3 with 0 probability. And given a probability distribution, given a preference, room 1, room 2, room 3, and 2 probability distribution, say 2/3, 1/3, 0, and 1/3, 1/3, 1/3. I will say one probability distribution stochastically dominates another if some condition is satisfied. Oh, sorry. If some, what is happening? If some condition is satisfied, this condition is satisfied. It basically says the probabilities of the top outcomes. So I will say P, the probability distribution P will stochastically dominate Q if the probability of any top set according to P is greater than equals to that in Q. Okay, I'm not sorry. I will not go into the details of this stochastic dominance. I'm just telling you is some game theoretic condition for the time. The question is and then I define strategy proofness as through first order stochastic dominance. So there is some first order stochastic dominance, which you know here is just a mathematical definition, and there is some property, and through which I am going to define some called strategy proof, some efficiency and strategy proofness, 2 properties. So I have a matching function. I'm defining 2 properties. One is called efficient. Efficient means that I will define the outcome in a way so that it cannot be improved for everyone. There is no other way to define the outcome which is better for everyone, strictly better for someone, and weakly better for everyone. That is prior to efficiency. And then we have also strategy proofness, which I have already discussed, is a game theoretic equilibrium condition. So the 2 conditions are there. Question is, very important question, is that is every random matching function, which is unanimous, strategy proof, and efficient, is a convex combination of deterministic matching function, which is efficient and strategy proof. You see, for instance, you know that bistochastic matrices is a set of bistochastic matrix. It is convex, and the extreme points are deterministic bistochastic matrix, and is a known result in linear algebra. You know it very well. But here we have functions. It's not one set of bistochastic matrices. We have a function from d to the power n or any finite set, 2 bistochastic matrices. Those functions are convex. So if you have 2 functions, if you consider a convex combination of the 2 functions, that is also efficient and strategy proof, that it can be shown. So we know we have a set of convex functions. We want to know the extreme points of that. It's a very important question in game theory. You call it extreme point characterization. It is not known. And I have been working on this problem like loosely. I could not make much progress, very honestly. I don't know whether some advanced result in mathematics will be helpful or not, but this is a very important problem. So summarizing, mathematically, this problem is that we have a convex set of equilibria. We want to characterize it by knowing its extreme points. We know it's convex, so what are the extreme points? The hope is that, is it true the extreme points are all deterministic? It's a very good news for game theory because deterministic rules are very easy to work with. If not, then what are all non-deterministic extreme points of this convex set? Because we want to know the equilibrium. Okay, so with that, I will stop. Thank you very, very, very much for the invitation, for giving me the opportunity to speak. I really wanted to make the mathematics and probability people aware of these game theory problems. I always, whenever I get a chance, I tell them. I did this to many of my teachers, including Professor K.R. Parthasarathi. Whenever I get a chance to talk, I always talk about many other problems I have. These are the problems that are perhaps fascinating or interesting for young students, but there are also advanced problems. So once again, thank you very much, everyone. And this is thank you, end of my talk.
Thank you so much, Souvik. So are there further questions? I know there were several during.
I have just one question about the implementability. Can you please go back to the slide on implementability? You have got Ti prime, right?
Hello, can you hear me?
Yeah, the implementability.
Sorry, because I was using my laptop and then I have switched to my tab. So once again.
Yeah, in the implementability, you have got Ti and Ti prime, right? Definition of implementability.
Yes. Just a second. Let me. Just a second. Let me. Give me 1 second. I'm having some technical issues. Very sorry. Okay, okay. 1 second. I'm very sorry. I have got some technical issues and I cannot hear you very clearly, but I can hear you. 1 second, please, sir.
No, but anyway, you don't have to show
Implementability.
you see, you don't have to show the slide. In the definition of implementability,
Yes.
you have Ti and Ti prime, but I is unnecessary there, right? For 2 points T and T prime, right?
Yes.
Okay.
Yes.
And secondly, in that condition, you have got F of Ti minus P of Ti, right?
Yes. So implementability means according to your true preference. So suppose you have some sincere preference which is your private information, which I cannot see. Implementability means that truth telling is a dominant strategy equilibrium. If you tell me the truth, if you report your preference truthfully, you will get some outcome. Now, if you report your preference falsely, but even if you report your preference falsely, you will evaluate the outcome according to your true preference. So that's why the true preference, the squiggle I will feature when you are doing the evaluation. I will determine the outcome based on your false preference, false report, but you will back to evaluate the outcome according to your true preference. So that's why when in the definition of implementability, the F will act on squiggle I prime, but you will evaluate it using your squiggle I. So the condition will involve squiggle I of F of squiggle I prime. Does it make it clear?
Okay.
Oh, I'm extremely sorry. I mean, I'm in a remote place. I'm using both my laptop and tab, and all of a sudden my laptop is went off. So I'm now switched back to tab, and so some problem. But I hope it's clear. I will. If I get a chance, I will discuss this thing with you.
No, I understand. Yeah. Okay, that's fine.
Okay.
Thank you.
Further questions? Okay, so if not, then let's thank the speaker again for the very nice talk. And line of line. Okay, so let me stop the recording now.